Hi there, this is Jude Socrates. Welcome to today's video where we will be learning an important technique for integration, which is called integration by parts. So in this video and in maybe the next 5 videos or so, we will be learning a lot of techniques that will enable us to find integrals. Okay, so let me show you what we're going to do today. We're basically going to look for several integrals. Here they are, 5 of them. Okay, so I mentioned earlier that we know how to find the derivative of ln of x, but we don't know its antiderivative. And the same thing for inverse sine. Okay, so integration by parts is going to allow us obviously to find these two basic integrals, which we don't know yet. But also it is powerful enough that it will enable us to find these 3 other integrals, okay, and of course a host of other integrals which are of similar form. Okay, so yeah, basically, of course, these two are products. Okay, so the integration by parts formula is loosely based on the product rule for derivatives. Okay, so far we do not have a product rule for integrals, and in fact we don't. Okay, so the integration by parts formula is the closest thing that we will get to a product rule for integrals. So let's learn about it and let's see how to apply it. Let's start with the product rule for derivatives. So we know that the derivative of a product u of x times v of x is the derivative of u of x multiplied by v of x added to u of x times the derivative of v of x. So everyone learned the product rule in basic calculus. Let's convert it to a differential form. So we are going to suppress the x variables. U and v, we will implicitly state that they are functions of x. So the differential of u times v is the differential of u times v plus u times the differential of v. So we don't have derivatives in this equation. We have differentials. What are we going to do? We are going to move one of the terms. So we have du times v plus u times dv on the right side. We are going to move the du times v to the other side and essentially isolate u times dv. Okay, so u times dv is the differential of u times v minus v times the differential of u. So we flip the factors when we move the du times v over to the other side. It's more naturally written as v times du. So now we can integrate both sides of this equation. The integral of u times dv is the integral of du times v minus the integral of v times du. But the integral of the differential is simply the symbol of what is inside the differential. So the integral of du times v is simply u times v. So we get on the right side this equation, integral of u times dv is u times v minus the integral of v times du. So that gives us the integration by parts formula. The integral of u times dv is u times v minus the integral of v times du. If you have limits, a definite integral from a to b, well, you can simply evaluate u times v at b and a and subtract as usual, and then subtract the integral from a to b of v times du. So how do you apply this formula to an actual integral? We have 5 integrals that we are going to compute. The key to success is to choose u and dv wisely. It's called integration by parts because you're basically looking at an integral and separating it into 2 parts. One of the parts is called u, one of the parts is called dv, and the dx obviously should go with dv all the time. So once you decide on who is going to be your u, who is going to be your v, to complete the formula, we need to find v from dv, and we need to find du from u. So once we do that, we will be left with another integral, but if we keep our fingers crossed, hopefully this second integral is going to be simpler than our original integral. Here we go. Let's look for the antiderivative, the general antiderivative of the natural logarithm. We have to partition our integrand into a u and a dv. Well, we don't have too many choices. Dx, we said, always goes with dv. So there has to be a dx over here. But we have only ln of x left, and could it go with the dx? Sure, but then u will just be 1. Okay, so it probably makes more sense that u should have the ln of x. Okay, so now that we have u is ln of x, we can solve for du. Okay, so what is du? The differential of ln of x is 1 over x dx. Okay, so don't forget that there is still a dx that goes with the du. So now what about dv? dv is dx, so v must be simply x. All right, so according to the integration by parts formula, the antiderivative of ln of x dx will be u times v. So we multiply u by v. It probably looks more natural if x goes in front. So we have x times ln of x. Let me put a multiplication symbol just for emphasis. Minus the integral of v du. Okay, so let me borrow the integral symbol here. Integral of v is x times du. Our du is 1 over x dx. Okay, and of course that's nice because this simplifies to just 1 times dx. So we get x ln of x minus the integral of dx. Well, we said earlier that the integral of dv is just v. The integral of dx is simply x. So this is simply going to be x ln of x minus x. And of course, we can put the plus c right there. All right, so we have a nice formula. The antiderivative, general antiderivative of ln of x dx is x ln of x minus x plus c. Whoops, sorry about that. Let's try again. Over here, and okay, there we go. We have a nice integral formula for ln of x. Next integral, we want an antiderivative for the inverse sine function. So just like ln of x, we don't have too many choices. The dx has to go with dv, no choice there. And we only have one other factor, inverse sine of x. Okay? We don't know the integral of that, so it doesn't make any sense to include that in dv. So let's try it with u. Obviously, that's what's going to work. So just like before, integrate dv, we're going to get v equals x. But what's the differential of u? We need the derivative of inverse sine. And I hope you remember that it is 1 over the square root of 1 minus x squared. So du comes with a dx. All right, so we have du and v. We are ready for the integration by parts formula. We said that integral of u dv is the product, oops, missed the x, is the product of u times v. So once again, v is x and should look better in front. X times sine x, u times v, minus the integral of v, v is here, du. So we need the integral of v times du. So let's copy our du over here. And our v is x. We will get an x over there. So this is a little bit more complicated than our previous example because we had just 1 over x times x dx. The x's cancel. Here the x's don't cancel, definitely. But, well, integration by parts is just another technique, another tool that we have to integrate. We still have known integral formulas. We still have u substitution, which by itself can be really powerful. And I hope you notice that, yeah, we can do a u substitution here. And you might say, well, u is already this and v is this, so maybe we need another letter. Fine. Let's pick w as our letter, as our substitution. So the worst part of this antiderivative is, of course, the square root of 1 minus x squared. So we have two choices, in my opinion. We can take the whole thing, square root of 1 minus x squared as our w, or just what is inside, 1 minus x squared. Now remember, our next step is going to be what is dw, and is it going to help us? Well, if we have the square root, the dw will have 1 over 2 radical yuck. Okay, so maybe we're better off using just the 1 minus x squared for our w. Okay, so let's try it. So dw is negative 2x times dx. Okay, so for emphasis, let's put a product sign there. Okay, and that's a good thing because x times dx shows up here. There's an x here and a dx. So this is the right choice for w. And we want x dx for our second integral. We get dw divided by negative 2. So let's put a fraction there. Let's write it as negative 1/2 of dw. All right, so we have this portion. Let's do it here. Okay, so let's just take this part and scroll up a little bit, get some room. So this is the antiderivative of our x dx becomes our negative 1/2 dw. Okay, so replace x dx by minus 1/2 dw. And 1 over radical 1 minus x squared, our 1 minus x squared is w. Okay, so you have square root of w in your denominator. So what do we get here? Well, we can take the negative 1/2 outside. I think it looks better like this. Minus 1/2. And we have integral of 1 over radical w, which is w to the minus 1/2. Okay, I don't know about you, but I always feel more comfortable when I'm applying the power rule and I see exactly what power I'm dealing with. Okay, so 1 over radical w is w to the power minus 1/2, right? So, power rule, u to the n plus 1 over n plus 1. Minus 1/2 plus 1 is positive 1/2. So, we still have a minus 1/2 on the outside, and we get a fraction, w to the positive 1/2, and divide by 1/2. Okay. So, what have we got? Well, 2 times 1/2, that just simplifies to 1, and we have the minus sign outside, so it's negative w to the 1/2, which simplifies to square root of w, negative square root of w. And our w is 1 minus x squared. So, yeah, let me do one more line, just so you see all the details. So this is equal to negative square root of 1 minus x squared. Okay, so that is the second term, which is over here. And it comes with its own negative sign. and that is because of the substitution that we did here and what happened when we solved for x dx. So we are ready to put it all together. Let's make a copy of this. So the first portion is, we don't need this part, is still x inverse sine of x minus the negative of square root of 1 minus x squared. So this turns into plus square root of 1 minus x squared. Okay, double negative. And of course, to be general, okay, we are going to put the plus c right there. Third example, now it gets a little interesting. We have two factors in our integral, and of course the dx. X squared e to the minus 5x dx. As usual, dx goes with the dv, but we have a couple of choices here. Who will go with u? Who will go with dv? Maybe both of them will go with u, but again, we're going to take a derivative to get du. So if we had both factors, you're going to need the product rule, and that's going to make it look worse, don't you think? So perhaps only one of these two factors should go with u, and the other should go with dv. Okay, but after we get u and dv, we need a derivative for du. We need an antiderivative to find v. If we put x squared with dx, the antiderivative will be x cubed over 3. The power just got bigger. But if you put x squared over here, the power is going to get smaller. So remember that the second integral that we get will have v du, and we want that second integral to be easier than the original problem. Otherwise, we're going nowhere. So it looks like maybe we should put x squared over here, and we should put e to the minus 5x over here. With those choices, du will be 2x times dx, and our v will be an antiderivative, so e to the minus 5x divided by negative 5. Okay, so if you're wondering about that, like where did that come from? Okay, fine. Let's integrate e to the minus 5x. Perhaps you have forgotten how to do that. It was in the end of one of our older videos. So we want to integrate that. Then we will use a small substitution. W equals minus 5x. So dw will be minus 5 dx, and dx is minus 1/5. Minus 1 over 5 dw. So this antiderivative is going to be the antiderivative of e to the minus 5x is e to the w, and our dx is minus 1/5 dw. Okay, so there's your 1/5, right? The minus 1/5 just goes out. Integral of e to the w dw will be e to the w. So we have minus 1/5. I'll just copy that. E to the w, which is over here. And bring back w. Our w is just minus 5x. So there is our antiderivative. Okay, so we are ready to plug that into our integration by parts formula. This antiderivative is, let me put this down a little bit, u times v. So we will multiply these two together. I think it will look nicer if we put the minus 1/5 ahead, and then the x squared, and then the e to the minus 5x. Okay, so that looks good because that is actually our integral. And then we subtract the integral of v du. So we are multiplying these two together, v du. So we get a minus 2/5. Let me borrow this. Parenthesis, minus 2/5. So I hope you see that that is going to turn positive. Okay, so the v du has a minus going with it. And then we have x dx times e to the minus 5x. So I think it would look good if we multiply e to the minus 5x to the right of x. All right, so this is good because from x squared e to the minus 5x, we are down to x e to the minus 5x. The power just got lower. That's usually a good sign. So if you like, let's just beautify this a little bit. So this is going to be plus 2/5. Just get that out of the way. All right, so now we want to apply the integration by parts formula again. I believe our last video was L'Hopital's rule. We saw that we can apply L'Hopital's rule as many times as we want. Same thing with the integration by parts. So we want to apply the integration by parts formula now to this. Okay, so I deliberately started at x squared because I knew that x will show up. I've been doing this for a while. So we will do something like this, except we have different factors. E to the minus 5x is still one of them. So it looks like we can probably recycle some of these ideas. But instead of x squared, we simply have x. Okay, so one part will be x, the other part will be e to the minus 5x dx with the same v by integrating. Our du will now simply be dx. Great. So now we can apply the integration by parts formula. This antiderivative is u times v. So we're going to multiply these two together. And I think we'll want the minus 1/5 like before. And x times e to the minus 5x. Okay, so that's u times v minus the integral of v du. Okay, so minus negative 1/5 integral of v du. So we will have integral of e to the minus 5x dx. And when you look at that, we are back to this, which we did, of course, just to get the dv. So we are ready to plug in everything. We have minus 1/5 x e to the minus 5x minus minus, that becomes plus 1/5. So let me borrow this. And that is a 1/5, not a 2/5. But we said that integral of e to the minus 5x dx is this, minus 1/5 e to the minus 5x. So let's copy this. Okay, fractions, negative signs, those are always dangerous. So let us simplify this. We can keep the first term, but the minus 1/5 times minus 1/5, that becomes a minus 1/25. Okay, there we go. Check one more time. That's minus 1/25 e to the minus 5x. Great. So we are now ready to plug that second integral back in here. So let's copy this, because if I scroll down, I will probably lose that line. Not yet. Almost there. Okay, so we want this copy here, and we want to replace this with this. All right. So we get, as our final antiderivative, this, and we multiply, we replace integral of x e to the minus 5x with this. So we will copy this and we will plug that in. Okay, so if you look, you know what, let's expand it, right? I was going to factor, but just to be safe, let's expand first. Okay, so many things going on here. 2/5 times minus 1/5. So that becomes a minus 2 over 25. Okay, but we have a 2/5 times minus 1 over 25. So that becomes minus 2 over 125. So carefully, let us remove the brackets. There we go. And let us make sure we have everything correct. Minus 2 over 25 for the second term. Minus 2 over 125 for the third term. Now, we can, of course, put the plus c over here and over here. And now, if you want, we can make this look a lot nicer by factoring out the e to the minus 5x. And how about the 1 over 25? Okay, so I will make a copy here. I will have a 1 over 125 and an e to the minus 5x. Factor them out. What is left of each term? I took out a 5, so I am left with, I should have a pay for it with 25 in the numerator. And I have a minus here. So minus 25x squared is for the first term. Check. Minus 25 over 125 is minus 1/5. And we have the x squared e to the minus 5x. Excellent. Next, we have a, oh, check it out. I did not realize that everyone has a minus term. So we can put a minus outside. Nobody said anything. Oh, that's right. I'm all by myself. Now, we have x e to the minus 5x. We have a minus 2/5. We took the minus out. Took out a 125. So out of the 25, I owe 5. I owe you $5. So 5 times 2 will be 10x. Check. Negative 10 over 125 is the same as minus 2 over 25. Finally, we have minus 2 over 125. We took out the minus 1 over 125, so we are left with plus 2. There you go. So that should be our antiderivative for x squared e to the minus 5x dx. Fourth example, we want the antiderivative for e to the 2x sine of 3x dx. And once again, our dx should go with a dv, and we have two factors to choose from. Earlier, we put e to the minus 5x with the dx, and we had x squared. Okay, but we have sine of 3x here. Sine of 3x also integrates nicely, right? So just for variety's sake, let's put the sine of 3x together with the dx. And let's put e to the 2x for our u. Just for some variety. What is du? Chain rule, 2e to the 2x dx. Integral, okay, integral of sine is negative cosine, but once again, we need a little substitution. W will be 3x, dw will be 3dx, dx is 1/3 dw, So we will have a 1/3 and negative cosine w. So negative 1/3 cosine of 3x. Okay, quick check. I did not write down the substitution. Instead, let's mentally do the differentiation to check that if this is our v, this should be the dv. Okay, so what is dv? Derivative of cosine is negative sine. So you got it. Negatives cancel. Negative sine of 3x. Chain rule, 3 goes out, cancels with the 1/3. Okay? So that is the correct differential. Okay, we have our du, 2e to the 2x dx from the chain rule. We are ready to plug that into our problem. U are u times v. So we are going to multiply e to the 2x times this. So we can take this and we have e to the 2x. Let's put the 2x, e to the 2x, to the left of cosine x. Minus v du. So this happened earlier. We had a minus sign in our v or du, doesn't matter. Minus, minus. Once again, we're going to get plus. Okay, so I'm going to skip that step where we have two negatives. Minus, minus, so plus, and then 2/3. Multiply the 2 and the 1/3. The constant is 2/3. And we get e to the 2x dx multiplied by cosine of 3x. So in the last example, x squared e to the minus 5x became x e to the minus 5x. It looks better. But now, we get e to the 2x cosine 3x dx, which does not look better or worse than e to the 2x sine of 3x. It's practically the same. So we are going to repeat integration by parts. And just like before, we can probably recycle some of our computations here. And you might think, maybe we're better off switching now. And no, there's no saying about changing horses in the middle of the stream. We're not going to do that, right? But we do have to make some changes because this time we have e to the 2x cosine 3x. So this should be a cosine. And we still have e to the 2x as one of the factors. Du is going to be the same, 2e to the 2x dx, but v, integral of cosine, is now positive sign, not negative sign. Okay? And we still have the 1/3 as before because of the little substitution. Mental check. The derivative of sine 3x is cosine 3x times 3, and the times 3 cancels with the 1/3 to give you cosine 3x. So that is the correct antiderivative to get v. So we want this, and as usual, let's take the 2/3 outside. Okay, I'm not going to do an extra step with that, but I will isolate this. So e to the 2x cosine 3x dx is u times v, so we will multiply these two together, and our u is e to the 2x, minus integral of v du. So minus of this product, v du, we will get a 2/3 just like before, but we will get an integral of v du. Oh, check it out. Sine of 3x e to the 2x dx. Wait, that is our original integral. See it? v du. So 2/3 goes out, but we have e to the 2x sine of 3x dx. So something funny is going on here, right? Let's look at the big picture. We want this, and in the first stage, first application of integration by parts, we got this for our answer. So let's copy that down here. In the second stage, we found this. And we said, oh, it's equal to this. So let me make a copy, just so you can see the changes. So this is now equal to this. So we get this over here. Very interesting. What is going on here? Let's distribute the 2/3 through the brackets. So we are going to get 2/3 times 1/3 is 2/9. We're going to put the 9 here. And we got that first factor accounted for. 2/3 times minus 2/3 is minus 4/9. And we are ready to erase the brackets. And as always, give it one more look. Minus 1/3, this doesn't change. 2/9 e to the 2x sine of 3x. Minus 4/9 integral of e to the 2x sine of 3x dx. Okay, so that distributes the right side. Where are we so far? This is the original integral that we are looking for. We said that it is equal to this. Okay, that's where we are so far. So this is where we do something a little bit different. Okay, we should definitely not do it one more time because it's going to end up with the same thing that happened before. Here's the smarter thing to do. Okay, so think of it as like an algebraic equation. I don't know who you are, but you're on the left side of this equation as well as on the right side. Okay, so let's give it a name. Let I be this integral. I for integral. I is this thing we are looking for. We don't know who you are. But the equation tells us that I on the left equals this on the right. But the last term is also I. Aha! So we have minus 4/9i right here. We're looking for I. So all we need is a little bit of algebra. Move the 4/9i to the left side. So I plus 4/9i must be these two terms over here. All right. And what's that? Well, I plus 4/9, 9 plus 4, 13/9. 13/9i must be this thing on the right. Ooh, awesome. So, clear the 9. We get 13i equals, 9 cancels partially with the 3. We're left with a minus 3 though. Minus 3 e to the 2x cosine 3x plus. 9 cancels with that 9, so that's going to be plus 2 e to the 2x sine of 3x. All right, and if you don't mind, let's factor out that e to the 2x. It'll look nicer that way. So we get e to the 2x times bracket negative 3 cosine of 2x plus 2 times sine of 3x. There you go. That looks a little bit nicer. Okay, so we are now ready to solve for I, which is what we are looking for. I, which is this, is equal to 1/13. Divide both sides by 13. 1/13 e to the 2x times minus 3 cosine 3x plus 2 sine 3x. There you go. And just for good measure, let's have the plus c. Final example, yay! Our last example in the list was this definite integral 0 to pi over 2 of sine to the 5th power dx. To solve this integral, we are going to do something a little bit more general. We want to find what's called a reduction formula for a power of sine of x. So obviously this power should be a positive integer, like 5. How are we going to do this? Well, we need integration by parts, and as usual, dx will go with dv. But, well, it looks like there's only one factor here, except no. There are n factors hiding here. If you have sine to the 5th power, you have 5 factors of sine hiding in your integral. So here's what we're going to do. We are going to borrow one of those sines. So sine of n, sine to the n of x is the same as sine to the n minus 1 times another factor of sine of x. Okay, I'm going to borrow the sine of x. So we will use that single power sine of x to go with dv. And we'll say, okay, the rest of you can go with u. U will be sine to the n minus 1 of x. So our du, power rule combined with the chain rule, the n minus 1 goes down. And then we decrease the power by 1. So we now get sine to the n minus 2 of x dx as usual. If dv is sine of x dx, then v should be negative cosine of x. Yes, the derivative of cosine is negative sine. We'll cancel the minus sign to produce just sine of x. Awesome. So now we can apply the integration by parts formula. Here, u times v. So we have sine to the n minus 1 of x times negative cosine x. Let's put the minus cosine x first. Minus cosine x times sine to the n minus 1 of x. Minus integral of v du. So there's that minus sign again, minus minus, so it will be a plus integral of, where's my integral sign? There you go. Of v du. So n minus 1, copy this, times a cosine of x. Oh, wait. I knew that something was missing. Something was missing because I missed one more application of the chain rule. Ooh, bad. We have sine to the n minus 2x, and one more. There's one more function inside. There's a sine of x. So we have a cosine of x. Okay. So we have cosine x and another cosine x. That should be cosine squared of x. Ooh, something was missing. There it is. So, yeah, quick check. Okay, minus has a plus, n minus 1, sine to the n minus 2, cosine, and another cosine is cosine squared. Now, what are we going to do? Well, we can rewrite cosine squared using the basic Pythagorean identity as 1 minus sine squared. Okay, so let's copy this. And let's take the n minus 1 outside, shall we? Plus n minus 1 times this. And, well, since we have copy paste, might as well do that. And then replace the cosine squared with 1 minus sine squared. So I will take this and turn the exponent to just sine squared x. Yay! And this is good because see what happens when we distribute the sine to the n minus 2x. It's still going on inside the integral. So the first term, let's put brackets here. The first term will be 1 times sine to the n minus 2, so that just goes away. And then minus sine to the n minus 2 times sine squared. The minus 2 and the plus 2 cancel out. So we have sine to the nx dx. And yes, we are back to where we started. Sine to the nx dx. It's hiding right there inside our integral. But this should remind you of what happened in our last example, where we saw e to the minus 3x minus 2x cosine 3x, whatever. It showed up again after the second step. So this, after one application of integration by parts, but helped out by the Pythagorean identity, we are back to where we started. We see our original integral. So we should distribute this integral out into two terms. So we have, I should have included that n minus 1. And integral of sine to the n minus 2x dx. Keyboard is not cooperating with me today. So n minus 2x, this is the first term, dx. And then minus another n minus 1, integral of sine to the nx dx, our original integral. Okay, as usual, quick check, n minus 1 sine to the n minus 2 minus n minus 1 integral sine to the nx dx. I think that's correct. Okay, and we said, okay, this came from the original problem, sine to the nx dx. So let's go back down. Big picture. The original problem becomes this on the right side. Yeah. The integral that we're looking for is all of this minus n minus 1 times the original integral that we are looking for. Exactly what happened to our last example. So let's call this integral I, and this is also I. We have minus n minus 1 I over here. So let I be, let's put in all the steps, just so you won't get lost once I ask you to do a problem. Left side is I, and on the right side we have this minus n minus 1 I. This is also I. All right, so we can move the term on the right to the left. I plus n minus 1 I will be all this stuff. But there's one main difference, though, in that we don't know what this integral is. However, the power is lower by 2. So if we start out with 5, this will now be 3. So this gives us something simpler, and we get to apply the formula one more time, this time where n is 3. That time around, 3 minus 2 is going to be 1. We're down to sine to the first power, just sine. We know how to integrate that in our sleep. Those are called nightmares. Okay, 1i plus n minus 1i, we just get ni, equals this right side. So now we get to divide both sides by n. All right, so final formula. We get I, which is this integral that we are looking for, is 1 over n, fraction going here, times negative cosine of x sine to the n minus 1x plus this thing. Okay, so that is our reduction formula. And you know what? Let's Let's highlight that. All right, so center stage, boom, there you go. And we're going to change the color just so we get nice, and now we'll do it later. Okay, so that is our reduction formula for sine to the power n of x dx. It's called reduction because the power goes down and you get a simpler, an easier integral that you can compute or apply the formula one more time. Okay, so we want apply this formula to find the definite integral from 0 to pi over 2 of sine to the 5th power dx. So our n is 5. So according to this formula, we will get 1/5, 1 over 5, minus cosine x sine to the 5 minus 1 to the 4th power of x. N minus 1 is 4. N minus 2 is 3. Oops, there we go, 3. And we evaluate from 0 to pi over 2. Okay, get over here. 0 to pi over 2. One small problem though, we don't know what this second integral is, but we get to apply the formula one more time. So it's like a subroutine, recursive subroutine for those computer geeks out there. What is integral sine to the 3rd power? So we will copy this now, and we will get 3. And 3 minus 1 is 2. And 3 minus 1 is 2. And sine to the n minus 2, that's just 1. Yay! So it's just integral of sine of x. And is that cosine or negative cosine? I believe it is negative cosine. So we have minus 2 cosine of x. Whew. Okay, so we will plug this answer in over here, right? So let's make a copy. Let's just copy that whole thing. The sine cubed will be replaced by this. So I'm gonna, let's put one more step. Where did that come from? Scoot. We will replace sine cubed of x, integral sine cubed of x, with this guy over here. Wow. Shall we do a little housekeeping? Yeah, let's do that. Let's do a little housekeeping. Let us distribute these fractions. And we get 4/3 minus 4/3 cosine x. So let's take that out. Minus 4/3 cosine x sine squared. And then let's make sure we see this correctly. So minus 2 gets distributed to the 1/3 and the 4. So that's minus 8/3. Minus 8/3 cosine of x. One more time. Minus 4/3 here, cosine sine squared. 4/3 times minus 2, minus 8/3. I think that's correct. So we are now ready to plug in the endpoints. At pi over 2, cosine of pi over 2 is 0, but cosine of x is everywhere. So we get 0 all over there. And then we plug in x is 0. But this time, sine of x is 0. Woohoo! So that goes away. That goes away. Cosine of 0 is not 0, though. So we get this last term, minus 8/3. Cosine 0 is 1. So that's minus 8/3 over there. And we get positive 8 over 3 divided by 5 times 1/5. We get 8 over 15. All right, and as a bonus treat, let's ask Maple. Maple, are you smart enough to compute this integral for us and check our work? And we get, yep, it is 8 over 15. That should be 15, the 5 times 3. Okay, great. So that is our video for today. I hope you enjoyed it. You're going to do some integrating by parts. You're going to look for an antiderivative for inverse tangent, perhaps, and a couple more problems. So, you got your work cut out for you. Until our next video, I hope you enjoy the rest of your day. Bye now.